So for periodic signals, we know how to analyze it using Fourier series representation. And for continuous time aperiodic signals, we have the Fourier transform. Okay? But we hope to be able to unify both of these techniques, right? Or at least have a Fourier transform analysis also for periodic signals, so that we don't have to switch between two tools when we're looking at different cases. Okay? So the question here is, can we also obtain a Fourier transform for periodic signals? Okay. So if we check through these previous conditions that we gave for the existence of Fourier transforms, those conditions actually do not hold for periodic signals, because periodic signals have neither finite energy nor are they absolutely integrable, right? Because periodic signals repeat themselves infinitely often. So when you look at the energy of the entire signal, it's definitely not finite, okay? But fortunately, we can still obtain a Fourier transform of this through a different perspective, okay? So the key idea is the following, right? So suppose that you have a spectrum, x of j omega, that is equal to a simple, unit impulse function, right? So this is 2 pi delta of omega minus omega naught. So if you use the inverse Fourier transform, you will find that the inverse Fourier transform of this actually corresponds to x of t that is a pure frequency component at the frequency omega naught, okay? So this is not hard to compute, right? When you plug this in, 2 pi cancels out. All right, you have delta of omega minus omega naught times e to the j omega t. So delta omega minus omega naught is non-zero only when omega is equal to omega naught. So you can replace this with e to the j omega naught t, okay? And then bring this outside. Then you have only integral over the delta function, which is 1. So eventually, you just have this exponential at frequency omega naught at the end, okay? And this relationship is also very intuitive, because in the time domain, when the time domain is this, right, this means that the time domain is just a pure frequency component at frequency omega naught, then you expect that the spectrum should be non-zero only at that value, okay? All right. So then, if you have a spectrum that is a linear combination of these unit impulses, then its Fourier transform will also be a linear combination of their corresponding frequency components, okay? Because each one of these has an inverse Fourier transform that is equal to this, okay? And we know that for every periodic signal, we can write it in this fashion, right? Which is the Fourier series representation, okay? And therefore, it has a Fourier transform that takes on this form. All right? So with this, we can have a unified Fourier transform treatment also for periodic signals. Okay. All right. So let's look at an example. So here we have an example of this periodic square wave. Okay. So recall that for this signal, x of t, that is a periodic square wave, it has a Fourier series representation, ak, that is sine k omega naught t1 over pi k, okay, where omega naught is 2 pi over t. Okay. So therefore, okay, its Fourier transform is the same linear combination okay, it's the same linear combination of delta functions at the corresponding frequency components. Okay, and AK was given above, right? We can just plug that in. This will give us summation I think I'm missing a let's see. Okay, I'm missing a 2 pi. All right, I should have a 2 pi here. Okay, so I'm missing a 2 pi. So this becomes summation 2 pi. AK is sine k omega naught t1 over pi k. Okay? All right. Now let me sort of rearrange this. All right, let me cancel out the common pi terms, multiply the denominator by omega naught, so I multiply it back outside, okay, so that nothing changes. Okay? So if you do that, then this thing here okay. So if you do that, then this thing here can be viewed as the sampling of the sinc function at omega equal to k omega naught. Okay? So, by adding an omega naught in the denominator, I multiply it out here so that they cancel out. Okay? But with this, I can then treat this term as the sampling of this sinc function, okay, at integer multiples of omega naught. Okay. So therefore, right, if you plot out x of j omega, what you see is actually these delta functions here, right? Sorry, I should multiply. Okay. So what you see is a bunch of these impulse functions, right, at integer multiples of omega naught, each one scaled by the value sampled from this sinc function, okay? So you have this envelope, right, that takes on the shape of 2 omega naught sine omega t1 over omega, okay? And you have these impulses that are scaled by the values sampled from this sinc pulse, okay? So this is the Fourier transform of the periodic square wave that we have up here. Okay. Now we can also look at some simpler examples. Okay. So here we have examples of these simple sinusoids. Okay. So for simple sinusoids, by Euler's relation, we can directly write them as a linear combination of complex exponentials. Right? So for sine omega naught t, this is 1 over 2j e to the j omega naught t minus e to the minus j omega naught t. Okay? Right. So you have this coefficient 1 over 2j at frequency omega naught and minus 1 over 2j at frequency minus omega naught. Okay. So we know the Fourier series coefficient are A1 equal to 1 over 2j and A minus 1, that is minus 1 over 2j, and AK equal to 0 for all k not equal to plus minus 1. Okay. So then the spectrum should be just a summation of two delta functions at the frequencies omega naught and minus omega naught respectively. Okay. So you should have 2 pi 1 over 2j delta omega minus omega naught minus 1 over 2j delta omega plus omega naught. Okay. All right. So if you plot this out, right? If you plot this out, this will give you, right? 2 cancels out. This will give you pi over j. Right, pi over j at frequency omega naught, right? So this corresponds to this impulse here, and this will give you minus pi over j at frequency minus omega naught, which is this. Okay. Okay, so this gives you pi over j minus pi over j omega plus omega naught. Okay? So this term is this, and this term is this. Right. So you can do the same thing for cosine, right? This is pretty straightforward. So let me just leave this for practice, okay? Okay. So one more example. Okay. So this last example is the impulse train. Okay, so here the time domain signal is a periodic impulse train. You have a unit impulse at integer multiples of capital T. Okay. So for this, right, the Fourier series coefficient AK, okay, it's just the integral okay, of this x of t, right, over one period. Okay, over one period. Okay. So to find the coefficient ak, you take 1 over t, the integral of x of t, times e to the minus jk omega naught t, integrated over one period. Okay. Right? So this is non-zero only when t is equal to 0. So if you substitute t equal to 0 inside here, this exponential becomes 1. So you're basically just integrating over a delta function, which gives you a constant 1. Okay. So eventually, this shows that, ak is 1 over t for all k. Okay. So therefore, x of j omega should be 2 pi over t summation delta omega minus 2 pi k over t for k from minus infinity to infinity. Okay? So ak is a constant 1 over t for all k. Right? So you just plug this. You just plug this inside the formula here, right? This is 1 over t, so you have 2 pi over capital T that is brought outside. So you just have a summation of delta omega minus k omega naught, okay? And omega naught is 2 pi over capital T. Okay. So this shows that if you have an impulse train in the time domain, you will also have an impulse train in the frequency domain. Okay. So if you, right, this is also an impulse train. Okay. So if you plot this out, okay, your frequency domain would also be this impulse train, each one scaled by 2 pi over t. Okay. So do we have any questions up to this point? Okay. So most of these examples are, pretty much, pretty straightforward, if you just apply the Fourier transform formula. Okay. So the reason I went through them one by one is because these are very common cases that you will see repeatedly later on. Okay. So you will see, repeatedly cases with, decaying exponentials, either one-sided or two-sided. You will see examples of a delta function. You will see square waves, right, which lead to sinc functions after the transform, okay? And, right, you will also utilize the property that impulse trains have a transform that is also an impulse train, okay? So all of these derivations, although are straightforward, right, these are examples that you will see repeatedly, and hopefully you can have some insight on these examples, okay? All right. Now some shorthand for